topic 5.1, Newton's law of gravitation. Let's see what is gravitation. Every point mass in the universe attracts every other point mass, and this attractive force is termed as gravitational force. Now let's see what is Newton's law of universal gravitation. Newton's law of gravitation states that every point mass attracts every other point mass by a force acting along the line intersecting the 2 points. The force is proportional to the product of the two masses and inversely proportional to the square of the distance between them. This can be written in mathematical form as follows. Here M1 and M2 are the 2 point masses in consideration. Distance between them is simple r. Then, as per Newton's law of universal gravitation, F is proportional to the product of M1 and M2, say equation 1, and also F is proportional to the inverse of the square of the distance between the 2 point masses, say equation 2. In combination of equations 1 and 2 and introducing a proportionality constant G, this can be written as this. This is the equation form of Newton's law of universal gravitation, where G is termed as the universal gravitational constant. If we subject G from that equation, G comes as this, and therefore the SI units of G will be as this, and dimensions of G is as this. Gravitational field intensity. If the gravitational force on an object of mass simple m in space is F, then we can see that F is proportional to m. Imagine a single point mass m exists in a space, and there is a gravitational force F on that point mass. Then we can see that F is proportional to m. By introducing a proportionality constant G, we can write this as F equals Gn. The proportionality constant G is termed as the gravitational field intensity. If we subject G equals F over m, therefore SI units of G is newtons per meter, and dimensions of G will be LT minus 2. Gravitational field intensity G can be defined as the force per unit mass due to gravitational field. Now let's consider the gravitational field around a spherical object of mass capital M. A spherical object of mass capital M can be treated as a point mass of capital M placed at the center of that spherical object. If we keep another point mass simple m at a distance simple r away from the center of that spherical object, and by applying the Newton's law of universal gravitation in between these two objects, we have following relationship. Say equation 1. But by definition of gravitational field in strength, we can also write, now combining the equations 1 and 2, we will have this expression for gravitational field intensity around a spherical mass of capital M. Since G and capital M are both constants, it follows that G is proportional to reciprocal of square of the distance to the simple M. Now, if we graphically represent the variation of gravitational field intensity around a point mass with the distance, and also around a spherical mass with distance from the center of the sphere, they will look like as follows. This is around a point mass, and this is around the outside of a spherical mass of capital M. Gravitational potential. Gravitational potential at a point in a gravitational field is the work done in bringing a unit mass from infinity to that point. Gravitational potential at a point of distance r away from a point mass capital A. If we imagine there exists a point mass capital M, the gravitational potential at a distance r away from the point mass M, V is given by minus gmr. The graphical representation of gravitational potential V with distance r from the center of the mass will be as follows. Since both G and M are constants, V is proportional to minus 1 over r. Therefore, the graph is like this. Gravitational potential at a point outside a spherical mass will also have the same relationship. And if we graphically represent that, it will look like as follows. Gravitational potential energy of a mass simple m in a gravitational field. Gravitational potential energy is the product of gravitational potential and mass. Therefore, the expression for gravitational potential energy of mass simple m in a gravitational field is given by this equation. Energy equation of a mass m moving with speed v in a circular path of radius r around a spherical mass capital M will be as follows. Imagine we have a spherical mass of capital M and a point mass simple m is orbiting around that spherical mass at a radius of simple r. Then total energy of this point mass m is equal to gravitational potential energy plus kinetic energy, which is given by this equation, can also be written as